Hello everyone, this is Essam and today I'm going to show you my IBM data science capstone project on state prediction in high storage systems. So enjoy.
Okay, so let's start. In the beginning, I would like to make some acknowledgements. Here is the download link for the dataset, and these are the references. The dataset I got is from kaggle.com, and it represents high storage system data. The libraries used throughout the project were scikit-learn, pandas, keras, matplotlib, and seaborn. The dataset includes 20 features and around 90,000 rows. The features are four conveyors and two rails with different parts of them. And here in this image, it represents the conveyors and the rails. The blue ones represent the conveyors, and the yellow ones represent the rails. What they do is that they basically transform packages from spot A to spot B, like here. This is a package, and this is how it moves. The dataset includes labeled data, where binary label data where the one represents faulty or broken records and the zero represents the healthy ones. So it's obvious that what we need to do now is that we need to cl classify records or to create a classification model that can predict whether a record is a healthy or broken one. These are some mathematical formulas applied on the data set. For example, here are the mean, standard deviation, and the count, for example, so on and so forth. Throughout the data exploration, it was discovered that there's a huge class imbalance, that we have around 80,000 um, healthy points and around 10,000 broken ones. This long line represents the healthy records and the shorter one represents the broken ones. Moving on throughout visualizing the data, the library Seaborn was used, and as we can see here, this represents a small deviation in the BLO vec, for example. So as here, this also represents a deviation. Here it's also a deviation. Here, so on and so forth. However, here in the HR, this represents similarity between the healthy and the broken records. So we can later on, in later stages when training or when feature engineering, we can actually ignore this feature when training the model. So, the feature engineering first, we had to check for null values, and thankfully none were found, zero known values. And as we mentioned earlier, we can now ignore or filter the O underscore W underscore HR underscore power feature. Dataset transformation was applied, and 20 features were transformed into three features using PCA for feature reduction. However, and these are the the representation with equivalent representation of the values here, PCA0, PCA1, PCA2, and this is the visual representation in three-dimensional space. And as we can see here, the yellow points represent the broken records. So, as I mentioned, it yielded less accuracy when applying on only three features. So iterative approaches were followed, and for example, 10 features were tried, 11, and so on and so forth. However, the accuracy was still low. So the solution was to just filter the O underscore HR underscore power because it decreased also the accuracy, and to just apply to apply or to train the model on the 19 features. Dataset normalization was also applied using the min-max scalar function, and for the class imbalance issue, the the healthy and the broken, a sample of 10,000 records was taken from each, the healthy and the broken records, and they were put together they were concatenated together into one pandas data frame, where the training was applied on this data frame later on. So the classification models used, or the classification approaches used, were the naive bias and the neural networks. Naive bias is a non-deep learning approach, classification approach, and the neural networks is a deep learning approach. Bernoulli naive bias was used and by the scikit-learn library. However, it yielded 59% of accuracy on the test data, which is not very satisfying in my opinion. So the Kira sequential model was also applied with the three layers, and the binary cross entropy for loss calculation was used. The ReLU and the sigmoid activation functions were applied. And these graphs represent the model accuracy on training and test data here. And here's the same, but for the loss. As we can see here, it yielded nearly 87% accuracy on training and on testing data. And the loss has reached around maybe 35% on test data, or a bit more, I think, and 20%, or I'm sorry, 32, 33% on the training data. So to wrap up, it was discovered that feature engineering was one of the most crucial tasks throughout the project, and the good understanding of the data can help identify the best use case. Of course, as we have seen, neural networks have yielded more than 25% increase in accuracy, and tuning the neural network can drastically enhance the performance, for example, by increasing the number of neurons or decreasing them, and so on and so forth.
Okay, thank you so much for watching and wish you a really nice day. Bye.